In this video, we will learn a very useful technique in geometric algebra, which is the use of geometric algebra products to eliminate variables in simultaneous equations. And up in the corner here, I will also put a link to a video that describes other solution techniques for different types of problems. In this video, we will use this technique of eliminating variables to find the intersection of two lines and also to detect when two lines are skewed and do not intersect. A common way of formulating a line in geometric algebra is to choose some point through which the line passes and also denote the direction of the line by means of a unit vector. So here this is schematically. Every point on this line, or I should say the vector from the origin to any point on this line, is a vector sum of this vector from the origin to the point plus some scalar multiple of the direction vector. And we'll play around with that here just a little bit. And importantly, lambda is a scalar. And we'll emphasize that, or I emphasize it here because it will be useful to us in determining whether lines are skewed. Of course, we can also denote or formulate a second line by the same means. In this case, any point on this line is the sum of this vector plus some scalar multiple of this direction vector. And what we're interested in finding out is where these two lines intersect. So the idea here is that the vector from the origin to that point of intersection is simultaneously the sum of this vector and some scalar multiple of this direction vector, and also the sum of this vector plus some scalar multiple of this direction vector. And I've used the asterisks here to denote that these are specific values of lambda and of gamma. So this is the idea. This vector is the sum of these two and also of these two. So let's write that out algebraically. This sum is equal to that sum. And we want to find out lambda star, and well, if we know lambda star, that's enough to find this point. So how can we eliminate gamma star? Well, the way we do that in geometric algebra is to take the outer product of u hat 2 with both sides. Now, why do we do that? Well, the outer product distributes over the sum of vectors. So we'd get u hat 2 wedged with a2 and u hat 2 wedged with a scalar multiple of the same u hat 2. Now, the wedge product or outer product of any vector with a scalar multiple of itself is 0. So when we distribute this here, we get u hat 2 wedge a2, and this part just is 0. And now you can find details of this in standard references or in the video that I'm going to link. When we're done simplifying this, we get lambda star times u hat wedge u1 is equal to u hat 2 wedge a2 minus a1. So we get a scalar multiple of a bivector is equal to another bivector. And the way that we solve this then is by multiplying both sides by the inverse of u hat 2 with u hat 1, or I should say this bivector. I apologize for that. So when we're done here, multiplying by the inverse of this bivector undoes this multiplication where we end up with just lambda star. And on this side, of course, we get this bivector multiplied by this one. The inverse of a bivector is a bivector itself, of course. So again, details on this can be found in a lot of standard references or in things that I've uploaded. So this is all nice, it's very efficient and convenient. But let's look at a case that at first glance is similar. Here we have two lines that are actually skewed. Now let's look at the solution that we came up for the lines that intersect. Lambda star is a scalar. But what happens in this case? Well, let's look in the three dimensions here. This bivector u hat wedged with a2 minus a1, this is a vector a2 minus a1. So this bivector u hat wedged with a2 minus a1 lies in this plane. In contrast, u hat 2 wedged with u1 lies in this plane. And the inverse of u hat 2 wedged with u hat 1 is a scalar multiple of this same bivector. So what we have here is a product of two bivectors that are not parallel. And in three-dimensional geometric algebra, the product of two non-parallel bivectors is not a scalar as it must be here. Instead, it's a sum of a scalar and another bivector. So if we had if we had this specific problem and tried to solve it this way, we'd carry out this product here of the two bivectors, and lo and behold, we'd find out that the result is not a scalar. It's a scalar, or it's a sum of a scalar and a bivector. And that would tell us that these two lines are actually skewed. So I hope this video rather, has been useful to you. In the description, I'll put a link to a LinkedIn group called Pre-University Geometric Algebra, which is dedicated to preparing instructional materials for teachers and newcomers and for students at the high school level. So I look forward to your comments and thank you for your time.